This will be Matthias Sperl.
So thank you very much for having me. And yeah, thank you much. I'm trying to explain to you a topic that will probably take longer time than I have here. So I embed into the slides the links both for the papers and for further material. So I also want to encourage you to download the PDF from the Google Drive, where I added some appendix for clarification. So next slide. When you talk about rheology, I wanted to go back and pick up what Karen had in the first talk. So this footprint on the moon is not just a footprint. Supposedly that was also done by Aldrin as sort of a proxy first rheology measurement on a foreign planet. And the challenge now is that we need rheological laws as basis for making up the processes up front, because we don't want to go to the moon or Mars and do trial and error for processes. Problem is that many empirical laws we developed in 1G may not work in anything else but 1G, and we don't even know if it works or doesn't. So our goal is to provide microscopic foundations for granular rheology that helps us go beyond empirical laws. We will do that with methods of liquid state theory, which I cannot explain in detail, but I give you the references. I will show you that the result compares excellently with rheological experiments, which is the first application of rheology in any case. And I will end with deriving some more handy constitutive laws from first principles. And I show, let's say, the angle of repose is one of these proxy methods that we want to go beyond. Next slide, please. So this is sort of to shock everyone that we deal with quite complicated equations. So one of the important things to remember is that we use memory equations. That's why we have integrals here. So it's not just easy equal sign algebraic constitutive laws, but in the end you can derive explicit formula for shear stress given by the shear rate. And if we focus on the right-hand side, you can, given the input of the microscopic interaction of the grains, calculate if you have Newtonian shear thinning or shear thickening behavior in your rheology. And on the left-hand side, I show you what I call flow curves, and that is what I will challenge with experiments in the next slide. And we have on the horizontal axis the shear rate. Note that this is on a logarithmic axis, and also on a logarithmic axis over a wide range, I give you the shear stress. Next slide, please. And using a novel fluidized bed rheometer, we produce on the big slide figure the data points, and we compare them to the same color theoretical curves. And you should appreciate that this works very nicely. Takes some rescaling and some shifting in the densities. And you can think of that experiment first as of a truly foundational rheology, but you could also interpret what you see here as the operation of a fluidized bed and getting the rheology out over many orders of magnitude. And I just wanted to flash on that this works quite nicely. Next slide, please. So one of the very famous laws in granular materials that you don't find in other rheology is the Bagnold law, that the shear stress for high enough velocities is proportional to the shear rate to the square. And I want to advertise that this can be calculated not only qualitatively, but we have a prefactor B for Bagnold, and we compare in the diagram the Bagnold parameter again on a logarithmic scale for different densities, and this works quite nicely. And we understand the deviations. On the left-hand side, Bagnold's experiment had a fluid, and on the right-hand side, we have jamming with permanent contacts. Next slide, please. question now, can we also derive and understand other empirical laws? And let's say on the empirical side for granular rheology, the mu of I, so the friction dependent on the inertial parameter rheology, is sort of the standard that you have to understand. It connects the shear stress with the pressure and has an important connection between mu and I, which I show here on the upper right-hand picture with a red curve, and the blue stars are repeated results of the theory I just showed you, and both the mu of I and the dependence of the packing fraction with I on the lower graph are matched reasonably well or almost perfectly, even if it's not a linear law, with the theory. Next, and I think last slide, I want to sum up that the flow curves that would go into process modeling for a fluidized system are described and predicted well by theory, can be changed from spherical particles to all kinds of shapes and forms in principle. Bagnall's law can be understood as mu of I from the theory quantitatively, and for a variation of density and shear rates, we find different numbers of rheological regimes that should be able to guide you when designing a process. Phenomenological laws, I just said that, can now be derived and put into context. Hello, doggy. And we hope that this will provide a reliable input for both quantitative calculations and qualitative understanding for the design of processes. And with that, I thank you for your patience and understanding.
All right, so actually we can take questions for Dr. Sperl right now, since we have a few minutes. I know people have been told to put them in the chat, but if you put them in the chat, I can read them out loud. So I will ask the first question then, since there isn't one there. So one of the things we've been seeing in the chat and in the conference is the importance of Coulomb forces. So do you have any idea how you might put that into this phenomenology?
Well, that's already the most dangerous question, because the Coulomb force is an unequal sign. So the fair answer is that no, we cannot do that right away, but you can include into that approach rotational degrees of freedom. And that, I think, is a fair proxy for many things. And you can fake it as additional decay channels for those correlation functions. So there's more elegant and less elegant ways. And if you do it really elegantly, I have yet no real idea how to put forward the Coulomb forces, but you can include the rotational degrees of freedom, so you may do well in applying that.
All right, thank you.